their paraffin increases and the roll of their weight increases. So it may lead to the candle should drown. But as you can see on this video, the candle remains on the surface for quite a long time. And in our solution, first we will understand why this happens, and then the theoretical part will approximate their time of burning, and then we will verify its time experimentally. And finally, we will do simulation, take into account the temperature distribution inside the candle, and compare all our results experimental. So, firstly, we have to understand that there are two different possible mechanisms why the candle remains on the surface for a long time. The first mechanism is more pronounced for thin candles. When the candle starts to drown, the surface tension force appears, and this surface tension force will lift the candles to the surface of water. And also, in the experiments with these, there is the initial fringe of solidified paraffin appears, and this fringe increases the buoyancy, so increases the time of burning in the water. Another mechanism is for the thick candles. For them, the cavity forms, so flame burns the cavity near the wick, so the average density decreases and the time of burning increases. Also, because their candle burns in the water, the heat conductance into the water, so their radius of the cavity decreases, and this means that their time of burning increases. Let's move on to the theoretical part, where we assume their shape of the cavity as a sphere, and also we found the volume of cavity from simple geometry consideration, and also there's the parameters PB and FB is the perimeter and area of the fringe. And to find the time of burning, we perform the force analysis. There are three forces acting on the system: the pressure force, which acts on the whole area of the fringe; the surface tension force, which depends on the perimeter of the fringe; and the gravity force, which acts on their candle and on their weight mass delta M. So, from the equilibrium condition, we obtain the minimum height of the candle still remains on the surface, and this limits the time of burning. Let's analyze the results. There are two terms. The first term is important for thin candles because there is their PB, the perimeter of the fringe. Also, there is a term which depends on the area of the fringe, so it's adds buoyancy. And there is a third term which is important for thick candles because delta V is their volume of cavity, and it is important for thick candles. And to verify this result experimentally, we need to investigate the parameters of the fringe, the rate of burning, and the radius of cavity, which defines the volume of cavity. Let's do it now. We start with the cavity, we burn the candle in water, let the profile to stabilize. Then we cut their candle along the axis and analyze the cavity in tracker. Here you see that we indeed can approximate the shape of the cavity as a sphere, and we obtain the dependence of the radius of cavity on radius of candle, and you see it doesn't depend on the radius of candle. We understand that it mainly depends on parameters of the wick and parameters of the material. For example, for a colorful candle, you see that the height of the flame is higher, so the radius of the cavity is higher too. And let's do the experiments on the fringe. We understand that it's important for thin candles and that the size of fringe changes on time. So firstly, we plot the dependence of the perimeter and area of the fringe on time, and we see that firstly there is a radius increasing, and then the size of the fringe saturates. And using this mechanism, we experimentally plot the dependence of the perimeter and area of the fringe on the radius of candle. And indeed, we see that this fringe is more important for thin candles, and for thick candles, only the narrowing along the perimeter of the candle appears. Then we experimentally find the rate of burning using tracker analysis, and here we plot the dependence of the rate of burning on the radius of the candle, and we see that with higher radius of the candle, the rate of burning is smaller. And so knowing these experiments, we can plot the dependence of the height of the candle, which can be maximum burnt on the radius of candle, and the time of burning. Here you see that as for the thin candles, for which the radius forms, and for the thick candles, there are a high time of burning. Let's verify the dependence experimentally. In experiments, we use their cylindrical vessel in which we put our candle with a rate, and also we use different candles with different radius, heights, properties of materials, and add the threads to the candle to not allow the candle flow along the surface of the water. So first we will change the height of the candle, and you see that the time of burning increases, and then when their height of the initial height of the candle is equal to the maximum height of the candle which can be burned, this dependence rate. And using this, we plotted the dependence of the height of the candle which can be burned on the radius of the candle, and also verify the dependence of the time of burning. Let's analyze this plot more deeply. For thin candles, because their size and range decreases, the time of burning decreases too, and then when the cavity forms, the time of burning increases. But you see that there is some deviation from theoretical prediction. It is the fact that there is no spherical cavity for thick candles. And for the huge candles, there is no spherical cavity at all, there are only white channel forms. So, to make our theory more accurate for especially thin candles, we did simulation. We take into account their heat release during first with the radiation of the flame, then the heat transmits by radiation in the air and absorbs by the surface of the candle. Then their heat transmits due to heat conductance. And finally, because there is the contact with environment, for example, with the water or air, the heat is diverted by convective heat transfer. Let's talk about our method of simulation to find the temperature distribution because the time of burning is about 10 hours or maybe higher. The candle volume varies slowly. So, knowing their initial profile of the candle and knowing the rate of burning in cosmology physics, we substitute the warming up, melting, and flowing down of the paraffin, so we find the final profile of the candle in their time about 10 minutes. So we diverted all our time of burning for some ranges about 10 minutes, and we found the final profile on all these stages, and so we determined their time of burning. To do it, we write down their heat equation, and we write down the necessary boundary condition on the inner surface of the candle, where epsilon is the degree of dampness of the paraffin, and also the necessary boundary condition on the outer surface of the candle, where we find their flow density transmitted by convection by Newton-Raphman's law. And so, to solve this equation numerically, we have to found their heat flux from the flame, which we did experimentally. Here is a plot on the vertical coordinates. So now we can solve our equations and in the cosmology physics, and also there we take into account the melting of the paraffin by reducing the phase in the candle. So let's analyze our results of simulation. Firstly, here you see the temperature distribution in the candle, which is burned in the air. And indeed, we see that the temperature in the borders of the candle is higher than the melting temperature of the paraffin. So this means that this candle wouldn't form the cavity in the air. But when we put in our simulation this candle in the water, because there is higher diverse of heat in the water, with this that the temperature in the boundary is smaller than the melting temperature of paraffin. So we see that in this case the candle will form the cavity. Let's verify all our results with experimental. Here we plotted the dependence of time of burning of the radius of the candle, and the blue curve is our theoretical prediction when we assume their shape of cavity as a sphere. And then green is our simulation. We see that it better correlates with experimental results, especially in the range for their thick candles for which there is no spherical